Have you ever wondered how the device you're using right now, your phone, your laptop, even the camera recording this video, can think, compute, and connect billions of people across the globe? Behind every screen, every processor, and every byte of data lies one of the most revolutionary branches of modern physics, solid-state physics and semiconductor physics. Welcome to the Learning Studio, and in today's episode from our physics playlist, we'll explore how the laws governing atoms and electrons in solid materials became the foundation of the digital age. You can watch the entire physics playlist by clicking the link below in the description. This topic is part of our new section, Matter, Materials, and the Rise of Technology, where we discover how the invisible dance of particles in matter gave birth to the technological world we live in today. From atoms to crystals, the birth of solid-state physics. It all begins with the question, what happens when billions of atoms come together to form a solid? In gases and liquids, atoms move freely, but in solids, they lock into repeating patterns, crystals, where each atom interacts with its neighbors in perfect geometric order. Inside these crystals, electrons don't just orbit atoms, they spread out, forming energy bands that determine how easily they can move. This discovery, the concept of energy bands and band gaps, gave birth to solid-state physics, the science of how atoms, electrons, and energy behave inside solid materials. Metals, insulators, and semiconductors are all defined by how their electrons fill these energy bands. And that's where the magic begins, in the semiconductors, where control over the movement of electrons allows us to control information itself. Semiconductors, the foundation of the digital world. Semiconductors are materials that are neither perfect conductors nor perfect insulators. Their conductivity can be finely tuned by temperature, impurities, or electric fields. The key lies in the band gap, a small energy window between the valence and conduction bands. When electrons gain just enough energy, they can jump this gap and move freely, carrying electric current. By carefully adding impurities, a process known as doping, scientists can create two types of semiconductors. N-type, where extra electrons increase conductivity. P-type, where missing electrons, or holes, carry positive charge. When these two types are joined together, they form a p-n junction, the heart of modern electronics. This simple interface powers diodes, transistors, LEDs, and solar cells, the building blocks of all modern technology. From the first transistor in 1947 to the billions of nanotransistors inside today's microchips, semiconductor physics has transformed the world, giving rise to computers, communication networks, and artificial intelligence. Quantum mechanics inside the chip. Deep inside every chip lies the invisible quantum world. Electrons behave not as particles, but as waves, tunneling through barriers and forming quantum wells that trap and manipulate energy. Solid-state physics merges quantum mechanics with materials science, explaining everything from the glow of an LED to the storage of data in flash memory. Even the materials used, like silicon, germanium, or gallium arsenide, are chosen for how their atomic structure shapes these quantum behaviors. It's a perfect marriage between physics and engineering, turning equations into devices that power our daily lives. AI, quantum devices, and the future of materials. But the story doesn't stop here. Today, AI and machine learning are revolutionizing semiconductor design. Instead of relying on trial and error, scientists use AI models to predict how new materials will behave, optimize chip performance, and even design quantum semiconductors, materials capable of processing information in quantum states. At the same time, solid-state quantum technologies, like quantum dots, superconducting circuits, and spintronic devices, are emerging as the next generation of computing components. They promise to bridge classical electronics with quantum computation, creating machines that are faster, smarter, and far more energy efficient. Even sustainability is becoming a frontier. Quantum thermodynamics, from our previous episode, meets solid-state physics here, driving innovations in low-power chips, green data centers, and renewable energy devices like high-efficiency solar panels and solid-state batteries. Why this field matters more than ever. Every time you touch a screen, send a message, or store a photo in the cloud, you're using the principles of solid-state and semiconductor physics. It's the field that transformed physics from theory into technology, from understanding nature to engineering the future. And as we move toward quantum computing, nanotechnology, and AI-driven design, this branch of physics is not slowing down, it's evolving faster than ever. This is the Learning Studio, and this was our episode on solid-state physics and semiconductor physics. If you enjoyed this deep dive into the science behind the technology that runs our world, make sure to subscribe, like, and check out our physics playlist linked below. In our next episode, we'll explore condensed matter physics and superconductivity, where matter takes on astonishing states that defy resistance and redefine the flow of energy itself. Because in physics, even in something as solid as a crystal, lies the foundation of everything that moves the future forward.